Somewhere in a physics classroom right now, a teacher is drawing tiny circles on a whiteboard, telling a room full of students that magnetism comes from electrons orbiting atoms like planets around the sun. It is a clean, confident explanation. It has been taught for generations. And it is not actually how magnetism works, not the way you are about to see proven, using an argument nearly 100 years old that most working adults have never once been shown. Pick up a magnet right now. Go on. You probably have one on your fridge, or clipped to a cable, or buried in a junk drawer somewhere near your keys. Hold it near a paperclip and watch it jump. You've done this 1,000 times since you were a kid. But here's the question that's going to unravel everything you think you know in the next 20 minutes. What physically is happening in that split second before the paperclip moves? Not the textbook answer, not magnetic field. The real answer, the one hiding underneath the diagrams in your high school science book, is stranger than almost anything else in physics. And for nearly a century, the greatest minds on Earth couldn't explain it using the laws that govern everything else in the universe. In fact, there's a theorem, one you've never been taught, that proves magnetism should be flatly impossible if you only use classical physics. And yet here you are, holding proof that it isn't. So something in our basic picture of reality is wrong. Today we are going to find out what. Let's start with the story you were told, because you need to understand it before we can take it apart. In school, you probably learned that a magnet is magnetic because electrons orbit the nucleus of an atom, and a moving electric charge creates a magnetic field, the same way a current flowing through a wire creates a field around it. Tiny orbiting electrons, tiny loops of current, tiny magnets, billions of them, all lined up in the same direction inside a chunk of iron, adding up to one big magnetic field you can feel with your own hand. It's a clean story. It's intuitive. It even shows up in slightly too confident YouTube explainers and outdated textbooks. There's just one problem. It's wrong. Not simplified, not close enough, wrong, in a way that physics itself proves. Here's the proof, and it has a name most people have never heard, even though it was worked out almost 100 years ago. The Bohr-van Leeuwen theorem. Two physicists, working independently, sat down and did something deceptively simple. They took the full machinery of classical physics, the same physics that predicts how planets orbit, how billiard balls collide, how currents flow through wires, and they asked it one question. Given everything we know about moving charges and orbits and fields, what net magnetism should a collection of classical particles produce, on average, at thermal equilibrium? The answer that came out of the math was 0. Not small, not negligible, exactly, precisely, mathematically 0. Classical physics, applied honestly and completely, predicts that magnetism cannot exist at all. No fridge magnets, no compass needles pointing north, no MRI machines, nothing. And yet you're holding a magnet in your hand right now that is very clearly disagreeing with two of the smartest physicists who ever worked the math. So pause here for a second and really sit with that, because this is the moment most documentaries skip past too quickly. This isn't a small gap in our understanding. This is classical physics, Newton's world, the world of solid orbiting particles and predictable forces, reaching into itself, doing the math honestly, and coming back with a flat, unambiguous, this should not happen. Something had to give, and what gave was our entire idea of what an electron actually is. Here's where it gets genuinely strange, and I want you to really picture this, because most people have never had it explained this clearly. Electrons have something called spin. For decades, this word has been badly, almost criminally, mistranslated to the public. You've probably pictured a tiny ball of charge literally spinning on its axis, like a marble twirling in place, the same way the Earth spins as it circles the Sun. That picture is comforting. It's also completely false, and physicists have known it's false since almost the moment the concept was introduced. If you tried to calculate how fast the surface of an electron would need to be spinning to produce the magnetic effect we actually measure, treating the electron as a tiny physical sphere, you'd need that surface to move many times faster than the speed of light. Since nothing can exceed the speed of light, the literal spinning ball picture breaks physics before you even finish the sentence. So what is spin, really, if it isn't spinning? Spin is what physicists call an intrinsic quantum property. And I know that phrase can sound like a dodge, like scientists throwing up their hands and saying, "It's just quantum, don't ask." But it's not a dodge, it's a precise statement. Spin is a fundamental attribute of a particle, exactly like mass or electric charge. You don't ask what makes an electron have negative charge, it simply does, as part of what an electron is. Spin works the same way. It's not motion, it's not rotation in any classical sense. It's an intrinsic form of angular momentum that the particle simply possesses, baked into its identity from the moment quantum field theory allows it to exist. And critically, this is the part that actually solves our paperclip mystery. This spin generates a magnetic moment. A tiny built-in magnetic north and south. Not because anything is physically spinning, but because that's what an electron fundamentally is. A small packet of quantum properties, one of which behaves exactly like an infinitesimally small bar magnet, with no moving parts required. Now here's your first misconception check, and I want you to actually guess before I tell you the answer, because this is where almost everyone gets it wrong, including plenty of confident adults who took physics in college. If every electron already has its own tiny magnetic moment from spin, why isn't every material on Earth magnetic? Why doesn't your wooden desk or your own hand act like a magnet? Take a second, guess. Here's the answer, and it's more elegant than most people expect. It's about pairing and cancellation, governed by a rule called the Pauli exclusion principle. In most atoms, electrons pair up inside their orbitals, and when they pair, their spins point in opposite directions, one up, one down, cancelling each other out almost perfectly. It's like two people pulling a rope with equal force in opposite directions. Enormous energy is present, but the net effect on the rope is zero motion. Most materials are built this way, atom after atom, electron pair after electron pair, magnetic moments quietly cancelling into nothing. That's why your wooden desk doesn't attract paperclips. It's not that its electrons lack spin, it's that their spins are locked in perfect, silent opposition. But a small handful of elements, iron, nickel, cobalt, a few of their close relatives and alloys, have an unusual quirk in their electron configuration. Some of their outer electrons remain unpaired. Their spins have no opposite partner to cancel against. Each atom of iron, structured this way, behaves like a tiny standing magnet all its own, with nothing to neutralize it. Take a moment and guess why iron specifically ends up with unpaired electrons in the first place, when so many of its neighbors on the periodic table don't. The answer lies in the particular arrangement of iron's outer electron shell, called the third subshell, which has room for 10 electrons across 5 available orbital slots, but, in iron's case, is only partially filled in a configuration that leaves several of those slots holding just one electron, rather than a full complementary pair. Quantum mechanical rules, specifically something called Hund's rule, actually favor spreading electrons out across separate orbitals with parallel, uncancelled spins whenever the energy cost of doing so is low enough, rather than forcing them to pair up prematurely. Iron, nickel and cobalt all sit in a region of the periodic table where this partial filling happens to leave a substantial number of spins unpaired, which is precisely why these three elements, among the vast majority of the periodic table, are the classic room temperature ferromagnets you actually encounter in daily life. And this is where the story usually ends in a simplified explanation. Unpaired electrons, so it's magnetic. But that's not actually the full answer to why a chunk of iron becomes a strong permanent magnet. Having unpaired spins scattered randomly throughout a material doesn't automatically produce a magnet you can pick up paperclips with. If every atom's unpaired spin pointed in a random direction, independent of its neighbors, the magnetism would still average out to almost nothing at the macroscopic scale. The same way a crowd of people all shouting different words creates only noise, not a chant. For a bar magnet to work, millions upon millions of these individual atomic magnets need to point in the same direction, in sync, cooperating across a scale utterly enormous compared to the atom itself. And explaining why they do that required physics to reach for something even stranger than spin itself. This is the part almost nobody outside a physics department has ever heard explained clearly, and it's arguably the real answer to the question in this video's title. The reason neighboring electron spins align with each other isn't a magnetic force at all. It's not one atom's tiny magnetic field reaching out and physically pulling its neighbor into alignment. The magnetic force between adjacent atoms is actually far too weak to explain the alignment we observe. Weaker by orders of magnitude than what's needed. The real reason is something called the exchange interaction, and it comes from an entirely different piece of quantum mechanics. The fact that electrons are indistinguishable particles, and the universe enforces strict rules about how their quantum states are allowed to overlap. When two electrons on neighboring atoms get close enough that their wave functions overlap, quantum mechanics imposes a symmetry requirement on their combined state. Depending on the details of that overlap, it can become energetically cheaper, genuinely lower in total energy, which nature always prefers, for those two electron spins to point in the same direction rather than opposite directions. This isn't a force pulling them together in the way gravity pulls a falling apple. It's a purely quantum statistical effect, a consequence of the rules identical particles must obey, that happens to produce the same practical outcome as if a force were aligning them. Physicists call the energy associated with this the exchange energy, and in materials like iron, it's strong enough to make parallel alignment the overwhelmingly preferred, lowest energy state across enormous neighborhoods of atoms. So here's the honest, complete version of the answer you came here for. Magnetism, at its root, is not caused by orbiting electrons acting like tiny current loops, the way you were taught. It is caused by the intrinsic quantum spin of electrons, which exists as a fundamental property with no classical analog, not a spinning ball, but a built-in quantum attribute. It exists in certain materials because some electrons remain unpaired, escaping the spin-canceling rule that neutralizes magnetism in most matter. And it becomes a large-scale, hand-holdable, paperclip-attracting force because of the exchange interaction, a subtle quantum statistical effect rooted in the indistinguishability of electrons, which locks enormous populations of these atomic magnets into cooperative alignment. Not one mechanism, three stacked on top of each other, each one purely quantum mechanical, each one with zero satisfying analog in the classical world you experience with your senses. The paperclip that jumped off your table did so because of an effect that cannot be explained, even in principle, without quantum mechanics. Bohr and van Leeuwen were right. Classical physics gives you zero magnetism. Nature simply isn't running on classical physics underneath the hood. Let's talk about how physicists even discovered spin existed in the first place, because the story itself tells you how strange and unwelcome this idea was when it first showed up. In the 1920s, two young Dutch physicists, George Uhlenbeck and Samuel Goudsmit, were trying to explain a strange doubling that kept appearing in the fine detail of atomic spectral lines, light emitted by atoms splitting into pairs of closely spaced lines where theory predicted only one. They proposed that the electron must carry an additional, previously unknown form of angular momentum, on top of whatever motion it had around the nucleus. Their own supervisor, the physicist Hendrik Lorentz, ran the numbers on the naive spinning ball picture and told them essentially, this cannot be physically real. The surface of such a particle would need to move faster than light. The paper had already been submitted by the time they heard this warning. Uhlenbeck reportedly wanted to withdraw it out of embarrassment. Their mentor, Paul Ehrenfest, told them not to worry, because they were young enough to afford a stupidity. It turned out not to be a stupidity at all. It turned out to be one of the most important discoveries in 20th century physics. Proof that nature contained a form of angular momentum with absolutely no equivalent anywhere in the classical world. Discovered almost by accident. Defended by two physicists young enough not to know it was supposed to be impossible. Now think about what that means for a second. The very people who discovered spin were initially terrified that they'd made an error, precisely because the classical picture screamed that what they were proposing couldn't exist. And yet the experimental evidence, those stubborn double spectral lines, refused to go away, no matter how carefully anyone rechecked the data. This is one of the clearest examples in the history of science of a mystery resolving itself not by explaining away the strange evidence, but by accepting that the evidence was right and the existing theory was incomplete. That pattern, trust the data, even when it contradicts your intuition, is exactly the standard we hold every case file on this channel to. Now, you might be thinking, alright, but there's a much simpler explanation for magnetism that I learned about, involving relativity and electric charge. And you're right to bring that up, because it's real and it deserves its own honest treatment rather than being brushed aside. There is a genuine, well-established sense in which magnetism can be understood as a relativistic side effect of electricity. If you have a wire carrying an electric current and you're standing still watching it, you'll measure a magnetic field around that wire. But if you were to move alongside the wire at the same velocity as the drifting electrons inside it, something remarkable happens in the mathematics of special relativity. What looked like a magnetic field from the stationary frame transforms mathematically into what looks like a modified electric field from your moving frame, due to length contraction affecting the relative charge densities of the positive lattice and the moving electrons. In other words, electricity and magnetism aren't two separate forces bolted together. They're two faces of a single underlying electromagnetic field, and which face you see depends entirely on how you, the observer, are moving relative to the charges involved. This is genuinely one of the most beautiful unifications in all of physics, and it's completely true. But, and this is important, this relativistic unification explains why a moving charge produces a magnetic effect. It does not on its own explain the intrinsic magnetism of an electron sitting perfectly still, the spin-based magnetism we just spent the last several minutes unpacking. That deeper layer requires quantum field theory, specifically the relativistic quantum equation developed by Paul Dirac, which, almost as a side effect of forcing quantum mechanics to obey the rules of special relativity, automatically predicts that electrons must carry both an intrinsic spin and an intrinsic magnetic moment, without either property being manually inserted into the theory. Dirac wasn't trying to explain magnetism when he wrote his equation. He was trying to make quantum mechanics compatible with relativity. Spin and magnetism fell out of the math as an unavoidable consequence, whether he wanted them or not. Few, if any, other moments in the history of science better capture the eerie experience of the mathematics of the universe simply refusing to let you avoid a conclusion. Push this one layer deeper still, into the theory that governs how electrons and magnetic fields actually interact at the most fundamental level physics currently offers. Quantum electrodynamics, often abbreviated QED, developed in the years following Dirac's work by physicists including Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. In QED, the magnetic force between two charged spinning particles isn't described as some invisible field simply reaching out through empty space. It's described as an exchange of virtual photons, particles of light that briefly flicker into existence, carry momentum and information between the two charges, and then vanish, never directly detectable, yet responsible for the entire measurable force. Every time that paperclip jumped toward your magnet at the start of this video, on the deepest level physics can currently describe, that motion was mediated by uncountable numbers of virtual photons passing between the electrons in the magnet and the electrons in the metal of the paperclip. And QED isn't a rough approximation waiting to be refined. It is, by a wide margin, the most precisely experimentally verified theory in the entire history of science. Predictions from QED about the magnetic moment of the electron match experimental measurements to better than 1 part in a trillion, an agreement so exact that physicists sometimes compare it to predicting the distance between New York and Los Angeles accurate to the width of a single human hair. When we tell you magnetism is fundamentally a quantum phenomenon, we're not describing a hunch or an elegant theory awaiting confirmation. We are describing one of the most rigorously tested claims that physics has ever produced. Let's also address the practical question that might be sitting in the back of your mind right now. If magnetism ultimately comes down to something as strange and invisible as quantum spin and exchange interactions, how does that connect to anything in the actual world you interact with daily? Consider the hard drive that may have stored your family's old photographs before everyone switched to the cloud. Every single bit of data on a traditional magnetic hard drive is stored using exactly the physics we just walked through. Microscopic regions of a magnetic film, each one a tiny domain of aligned electron spins, flipped between two orientations to represent a 1 or a 0. When you deleted a file and thought it vanished, what actually happened at the physical level was that a read-write head reversed the spin alignment in a specific microscopic patch of material, using the same exchange-driven cooperative behavior we described in iron. Consider also the MRI machine, a piece of medical equipment that has scanned millions of human bodies without a single incision. It doesn't work by detecting ferromagnetism at all. It works by manipulating the intrinsic spin of hydrogen nuclei in the water molecules throughout your body, using a powerful external magnetic field to align those spins, and then measuring the signal released as they snap back out of alignment. That signal, translated into an image, is what lets a doctor see inside your body without cutting it open. Every MRI scan ever performed is a direct working application of the exact intrinsic quantum spin property we've spent this entire investigation unpacking. This isn't abstract ivory tower physics disconnected from your life. It is, quite literally, inside the walls of your nearest hospital. And it isn't only heat that can break this cooperative alignment. Mechanical shock works too, which is why old sailors and machinists have long known that dropping or hammering a magnetized tool can weaken its magnetism over time, even without any change in temperature at all. The physical jolt disturbs the delicate domain structure inside the metal, nudging some regions of aligned spins out of formation. The same underlying fragility, just triggered by a different kind of disruption. There's also the question of why a permanent magnet can lose its magnetism entirely if you heat it up enough, which connects directly back to the exchange interaction we described. Every ferromagnetic material has what's called a Curie temperature, named after Pierre Curie, who first characterized this behavior experimentally. Below that temperature, the exchange interaction is strong enough to keep neighboring atomic spins locked into cooperative alignment, despite the random thermal jostling every atom experiences. Heat a piece of iron past its Curie temperature, a little over 1043 degrees on the Kelvin scale, or roughly 770 degrees Celsius, and the thermal energy shaking each atom becomes stronger than the exchange energy holding the spins in formation. The cooperative alignment collapses into disorder, domain by domain, and the material simply stops being a magnet, even though every individual electron inside it still has exactly the same spin it always did. Nothing about the electrons changed. What changed was whether they could stay organized against the chaos of heat. Cool the material back down, and in most cases the alignment reasserts itself and the magnetism returns, because the underlying quantum mechanism was never destroyed, only temporarily overwhelmed. There's one more layer worth being honest with you about, since this channel exists to resolve mysteries rather than leave you with more sensational, unanswered questions. Even the exchange interaction explanation of ferromagnetism, the mechanism we described in iron, nickel, and cobalt, has limits. It explains beautifully why nearby atoms align, but the full first principles quantum mechanical calculation of exactly why iron's specific electron configuration produces such strong alignment versus why a very similar element down the periodic table doesn't involves genuinely difficult many-body quantum mechanics that researchers are still refining with modern computational methods. This isn't a gap that undermines anything we've told you tonight. The core mechanism, spin, unpaired electrons, and exchange interaction is solid, well-tested, experimentally confirmed physics, not speculation. But the precise quantitative details, atom by atom, element by element, remain an active area of condensed matter research even now. That's the honest state of the science, not a mystery being hand-waved away, but a frontier being actively worked on by physicists using tools Bohr and van Leeuwen never had access to. Let's run the reality check on everything you've heard tonight, because that's what this channel exists to do. Not just present a mystery, but resolve it against the actual evidence. Myth. Magnetism comes from electrons physically orbiting the nucleus like tiny planets, creating current loops. Reality. This picture, called the Bohr model current loop explanation, cannot survive contact with the Bohr-van Leeuwen theorem, and the dominant contribution to magnetism in ferromagnetic materials comes overwhelmingly from intrinsic electron spin, not orbital motion. Myth. Spin means the electron is literally spinning like a tiny ball. Reality. Treating the electron as a physically rotating sphere requires surface speeds faster than light, which is physically impossible, so spin must be understood as a fundamental intrinsic quantum property, with no true classical counterpart. Myth. Nearby atomic magnets align because their magnetic fields pull on each other. Reality. The direct magnetic dipole force between neighboring atoms is far too weak to produce the alignment we observe, and the true cause is the exchange interaction, a quantum statistical effect arising from electron indistinguishability, which happens to favor parallel spin alignment as the lowest energy configuration. Every one of these corrections is backed by experimentally verified physics, not by educated guessing. That's the standard this channel holds itself to on every single case file. Before we close this file, I want to be honest with you about something else, because you've stuck with me through 15+ minutes of genuinely dense quantum mechanics, and that kind of attention deserves respect, not just a scripted thank you. Building an episode like this takes an enormous amount of research, cross-checking peer-reviewed physics, verifying that every claim, especially the more surprising ones like the Bohr-van Leeuwen theorem, is grounded in real, citable science, rather than the kind of oversimplified explanation that spreads easily online because it sounds satisfying rather than because it's true. If this kind of evidence-first, myth versus reality investigation is something you value, a super thanks genuinely helps keep this research process going at the depth you're seeing tonight. And I want you to know that whether you do or don't, I'm deeply grateful you spend your time here with us. This isn't a channel chasing sensationalism for clicks. It's a case file, and you're part of the investigation every time you show up. So here's where I want to leave you, because a good case file doesn't just close, it points you toward the next one. We've now established that ordinary magnets, the kind on your fridge, rely on cooperative alignment of electron spins across countless atoms, held together by the exchange interaction. But there is a class of objects in the universe where this entire picture gets pushed to a breaking point that our current condensed matter theories still struggle to fully explain. Magnetars, the collapsed cores of dead stars, generating magnetic fields so extreme, quadrillions of times stronger than Earth's, that the simple domain alignment story we told you tonight cannot survive unmodified in that environment. What actually happens to electron spin, to exchange interactions, to the very structure of matter itself, inside a magnetic field so powerful it would rearrange the electron clouds of atoms into thin, cigar-shaped distortions unlike anything found naturally on Earth? Think back, for a moment, to everything this file actually proved tonight, because it's worth holding on to. A theorem, decades old, showing classical physics predicts zero magnetism. A property called spin, discovered almost by accident by two young physicists brave enough to trust strange data over comfortable intuition. A quantum rule of exclusion, quietly cancelling magnetism in almost everything you touch. A rare exception in a handful of elements, driven by orbital arrangement rather than accident. And an interaction, not a force, an interaction, born purely from the fact that electrons cannot be told apart from one another, locking millions of atoms into silent, cooperative formation. Every one of those pieces was required. Remove any single one, and the paperclip stays exactly where it is. That's not a metaphor for how complicated physics can be. That's the literal, verified structure of why the object in your hand right now works at all. That's the next file, and I think you're going to want to be there when we open it.